Good day, everyone. Today we are going to be taking a look at the notes for section 5.2, Work, Power, and Energy. Now, up to this point, we have already talked about the different types of energy that exist in the world. But today, as we take a look at work and power, we're going to see how the different energy forms change. So we're first going to start by reinforcing the idea of what mechanical energy is. Previously, we knew mechanical energy was the amount of energy that an object possessed in the form of either potential energy or kinetic energy. Well, that total amount of mechanical energy is also the ability of an object to do work. And so we're going to take a look at what that work quantity is today. Well, work in and of itself is simply the transfer of energy into or out of a mass. Now, this seems a little bit like circular logic. What is energy? The ability to do work. What is work? It's the transfer of that energy. But ultimately, it's important to remember that they are related terms to one another. Work is simply what we call the act of transferring energy. This means that work can be positive or negative. Work itself is a scalar quantity, so it doesn't have a direction in terms of up, down, left, right, north, or south, but it does express an increase or a decrease because it is by its nature a change. Now, work will occur whenever a force is applied in the same dimension of the displacement of an object. So the object has to move in order for work to be done. So we can calculate work in a couple of different ways. The first one can be that we look at work as simply being the change in the energy of an object. And remember that the change of energy that an object undergoes is always its final energy minus its initial energy. So here's where the positive or negative can come in. If you have more final than initial energy, you get a positive work. If it's the other way around and you have less final energy, you have a negative work. We can also calculate the work by multiplying the force by the distance that the object moves. They do have to be in the same dimension, though. So, for instance, a waiter who holds a tray of glasses pressing upwards on the tray will not do any work if he walks to the right or left, because the force and the displacement are in different dimensions. And there's one small adjustment to this calculation if we are moving the object vertically, and that is the force is the weight. So mass times gravity, well, that's the weight of the object, and the height is the distance. So it's still the same formula, it's just expressed in a slightly different way. Now, power is a related quantity. Power is the rate at which work is done. So, rate means a change relative to time. Work is already the change in energy. So power is just simply the amount of work done divided by however long it takes for that change to occur. Power shows us how quickly the energy is transferred, while work shows us how much energy is transferred. One of the most common misconceptions is that a lot of power equals more work. That's not necessarily true. You can have a great deal of power But if that power is only active for a short period of time, not a lot of energy is transferred. Meanwhile, something with a low power, if it is continually working for a long period of time, will transfer an awful lot of energy. And so the next thing we want to take a look at are our units. Now, our units for work and energy are the joule, and we've seen that one before. The only true new unit here is the unit of the watt, which comes from dividing joules by seconds. So let's take a look at some examples. Our first example reads, a 40-kilogram box is pushed 8 meters across the floor with 12 newtons of force. How much work was done? In terms of solving any problem, once we have read it, the first thing is going to be to state our givens. So we observe a mass of 40 kilograms. We see a distance here of 8 meters. How do we know this is a distance and not a height? Well, it is across the floor. So it's not described as vertical, it's described as horizontal. The force is 12 newtons. So in terms of calculating the work, we are going to use the horizontal equation of force times distance, because we know that this is a horizontal force, because it's pushed across the floor. So this one, luckily, is by and large just a plug and chug. I don't know where that line came from, but we're just going to run with this. 12 newtons times 8 meters. The work done is 96 joules. Example 2. A 30-kilogram box is lifted 14 meters into the air. How much work was done? Just like before, we start by stating the givens. The first thing we are given is the mass, 30 kilograms. It's lifted 14 meters into the air. Now, because it's being lifted into the air, this means that the work that's being done is going to be our vertical equation, weight times height. And for simplicity's sake, I'm going to use gravity as 10 meters per second squared. And it's just a plug and chug. So going to our calculator, 30 times 10 times 14, 4,200 joules of work. A 45-kilogram crate has 200 joules of energy. If a force acts against the crate with negative 30 newtons of force, how far does the crate have to be pushed in order to remove all of the energy? All right, so this one has a couple more things going on to it. But our first thing that we always want to do is state our given information. We know the mass, 45 kilograms. Now we know that the starting energy is 200 joules. How do we know that's the starting energy? The crate has that much energy. So because we're observing the past tense, this means that it was the initial state. And since we want to remove all the energy at the end, this gives us the final energy of 0. Now the force that acts on the crate is negative 30 newtons. Now if you notice, we do not have the work. So we're going to have to calculate the work here using the change in energy. Final minus initial. As you may have guessed, this results in negative 200 joules of work, which we're going to use with our horizontal motion equation, force times distance, and we're going to divide both sides by the force to get the distance by itself. Because the question is, how far does the crate have to be pushed? We're looking for the distance. So negative 200 joules divided by negative 30 newtons. Note that the negative signs will go away. And we get a distance of 6.7 meters. Now we're going to start bringing in some power. A 55 kilogram crate is lifted 18 meters into the air over the course of 1 minute. How much work was done, and what is the power? As before, the first step is always state your givens. Mass, 55 kilograms. Lifted 18 meters into the air. That is the height. Over the course of 1 minute, that's the time. Now, 1 minute, we know that is 60 seconds. So we can kind of do that conversion right away. There's 2 questions for us to answer here. The first one is, what is the work? We're moving vertically, so it's mass times gravity times height. 55 times 10 times 18 will give us 9,900 joules. I can speak clearly, I swear. And that gives us the amount of work done. So now we have to calculate the power. Well, power is always work divided by time. So we're just going to divide that 9,900 joules by our time of 60 seconds. And this gives us a nice 165 watts of power. In this example, a light bulb is rated as 60 watts. This tells us how much electrical energy is transferred into light energy. If the light bulb is on for 1 hour, how much energy was used? Now, this is where there can be some confusion. It's asking us how much energy was used. But if we notice the problem, it tells us we have electrical energy transferred into light energy. So really what they're asking us to get here is the work that was done. So the power is 60 watts, and the time is 1 hour, which from our earlier conversions, we know is 3,600 seconds. Power is work divided by time. Multiply both sides by time, and we see that work is power times time. 60 watts times 3,600 seconds, and we see that the work done, aka the amount of energy used, is 216,000 joules of energy.